Okay, so welcome back to another video. So today's video is just going to be a simple calculation / evaluation. We want to just find the square root of 1 plus 2i is equal to I being the imaginary unit. So I think this is a perfect exercise for when you're learning into the whole introduction to complex analysis, when you're in the beginning of the curriculum learning about how complex number works and the representation, but also behind the algebra including. So I know this looks like a problem like this is not really deemed worthy of a video to show, but I feel like it is mainly because the value of, the given that we are trying to solve for is actually a very special value, as you can already guess from your the title of the video, that you can really guess your assumptions from there, what it's going to be. So essentially is a lot of just, introduction exercise and learning about complex numbers, how work, just mainly with, the point representation of complex numbers and using the algebra behind it. One of them we'll be using Euler's formula to rewrite some things, and then eventually it'll come down to a nice, beautiful answer. So with that, let's actually just start off by graphing what the 1 plus 2i is in the world of the complex plane. Okay, so here's the complex plane. Our x-axis in this situation, we call that's the real axis, and then the y-axis, we call that the imaginary axis. So what we want to do first is graph along the point of 1 plus 2i. So that means 1 plus 2i, or 1, 2 in the complex coordinates, is graph in this situation. So that means over here we have it goes by 1, and then down by this horizontally, this is 2i. So now how we want to find what the representation that is specifically is, and we know that for any complex number z in the representation of the form x plus I, y can be represented in the following polar form, r being the radius of the length of the distance, and then multiply with e to the power I times theta, theta being the measure of the angle right over here from the real axis all the way up to where the line is being drawn out. And so I have to label r over here for our length of our point. Pretty straightforward from there. We know how to calculate the distance from here. This is just basically just 1 square plus 2 square. Add those together and then take the square root of that. So I have 1 square plus 2 square. This is just equal to just the square root of 5. So we know what the radius is. Okay, and so now going even further, that if we just put everything together, so 1 plus 2i simply is supposed to be the square root of 5 and then times e to the power I theta, then we'll write this in the exponent form, so 1/2. So in other words, that's the same thing as written as, so distribute the 1/2 to the square root of 5. In other words, that's the same thing as the 4th root of 5, and then multiply with e to the power I and then theta divided by 2. So now we actually have to exactly find what the measure of theta is equal to. Well, luckily, thankfully, we already know what the radius is, and we already know what the length of the real axis and the imaginary axis is. So this is pretty straightforward and easy to say that. Now specifically, we'll measure this in terms of for cosine theta. Then that means we take the adjacent, so that's just 1, and then divided by our hypotenuse, which we solve for, that is the square root of 5. So cosine of theta is equal to 1 divided by the square root of 5. Another thing to do is we want to expand our e to the power I theta over 2, so just use Euler's formula. So we know that e to the power I theta over 2 is, in other words, the same thing as cosine of theta over 2. Add this with I times sine of theta over 2. And then another thing we need to keep in mind is that, well, before we get to that, let's just actually substitute this back in. So that's still the radius, so I can still factor this out either way. We haven't distributed anything yet exactly. So I have the 4th root of 5, and then multiply with cosine of theta 2, or theta over 2, and then add this with I times sine of theta over 2. Some things to keep in mind is that we have to figure out cosine theta 2 and then sine of theta over 2. Well, luckily what we can use is we can actually use the half angle formula that says the following. We have that cosine of theta over 2 is equal to the square root of 1 plus, keep in mind we have the radical, so we have to deal with plus and minus. So 1 plus cosine theta, then divided by 2. And then we have another one is that sine of theta over 2 is equal to plus or minus the square root of 1 subtract cosine of theta divided by 2. Now, of course, going back from earlier, we could have do something for sine theta and then solve for the values from there, but cosine theta is a little bit easier to solve for. Specifically for this reason, we want to plug in the values back in. Now, also keep in mind this because we have a plus or minus for the radicals, but thankfully, we actually graph what 1 plus 2i is, and it's only in the first quadrant, so therefore, we just only need to focus on just the positive value. So we'll be just looking at the positive square root of this value, and then the positive the square root of that value. So things makes the leverage a little bit easier to work around with. So therefore, now we have the 4th root of 5. And then now instead substitute cosine theta over 2 for here. So I have the square root of 1 plus cosine of theta divided by 2. And then add this with I times the square root of 1 plus cosine, well rather 1 minus cosine theta, then divided by 2. And then thankfully we already found what that value of cosine theta is equal to, 1 divided by square root of 5. So we'll just substitute this back in. So that means now I have the square root of 1 plus 1 divided by the square root of 5 and then divided by 2 plus I times the square root of 1 subtract 1 divided by the square root of 5 divided by 2. And then we can simplify this even further, that if I move the 4th root of 5 back into the square root, so that means that'll just reduce that to just the square root, then that means I have to distribute everything into the numerator, and so therefore leaving us with just the square root of 5, add this with 1 divided by 2, and then add this with I times the square root of 5, subtract 1 divided by 2. And I said that this is a special value. If you notice that from this side, this is actually the golden ratio number, so that can be reduced to write as the square root of the golden ratio number phi. And then over here, this is actually just the reciprocal of that. So add this with I times the square root of 1 divided by phi. And so therefore, that is our final answer to the square root of 1 plus 2i, that special value that is indeed an amazing, exercise just like that. So yeah, that's pretty cool if you ask me.